This is Vodcast 6A. In Unit 6, we're going to learn all about covalent bonds and molecular forces. Specifically, we're going to learn what is a covalent bond. We're going to learn how to draw and name covalently bonded molecules, as well as talk about molecular shapes and angles. First things first. Last unit, Unit 5, we talked about ionic bonds. Ionic bonds transfer electrons. They give and they take. Somebody, the cation, will give its electrons to another element or atom, an anion, who wants to accept those electrons. Covalent bonds are slightly different. They share their electrons between the two atoms. How does this happen? Well, you have two nuclei right here with their protons and their neutrons. Then you have two electron clouds. These two electron clouds both have a negative charge, but both of the nuclei have a positive charge. So how do I share these electrons? If they're both negatively charged, they want to repel each other. But each nucleus wants to attract the other electrons, since they're opposite charges. So what actually happens, they share their electrons by forming a cloud. So again, here's my kind of sharing the nucleus, and then these electrons on the outside are shared between the two atoms. Now, this is called a molecular orbital. They are covalently bonded, and they share one pair of electrons. A pair is two electrons. So each single bond that's covalently bonded shares two electrons. It's one pair. Here's another diagram that shows, this is my energy level, so this will be very high energy up here. This will be very low, this will be the lowest energy spot right here. And at this lowest energy spot, there's a perfect length for the bond, for where the two nuclei are exactly at a perfect distance apart from one another. If the nuclei get too close, they're both positive, remember, they want to repel, that increases the energy. If the nuclei get too far away, they can't actually share their electrons. That's also less stable. Less stable means more energy. So the potential energy, as the two atoms approach each other, the potential energy decreases until they are super duper stable. Right here at this point is where they're the most stable with the lowest possible energy. At that very stable point is the perfect length for each bond of those two elements that are bonding together. And this would be the energy of the bond, or the energy required to break the bond, right here at this perfectly stable point. So, some general trends about bonds. Greater bond energy is a stronger bond. It will require more energy to break the bond. It's therefore stronger. Stronger bonds are shorter. If you think of a pencil and you have a regular pencil that hasn't even been sharpened and you try and break it, it's pretty easy. But as your pencil gets shorter and shorter, it's harder to break. It's stronger. A multiple bond, this would be a double or a triple bond. Those are even stronger yet. Think about putting three pencils together and trying to break them. Double bonds, if a single bonds share two electrons each, a double bond would share a total of 4 electrons, and a triple bond would share a total of 6 electrons. So here's a chart with some trends. These are the different elements and who they might bond with. This is their average length, so the size of the bond, and then the average energy, the amount of energy required to break the bond. So as you can see, if my length increases, it gets bigger, it's easier to break. It requires less energy. So here's two questions for you. See if we can read this chart. Which bond is stronger, HBr or HCl? We're looking at these two right here. I can answer this question in two different ways. Which is the stronger bond? So the stronger bond would require more energy. Here's a higher energy number that says HCl is stronger. Stronger bonds are also shorter, so I can look at the length. Again, HCl has a shorter length, therefore it would be stronger. Question number 2. Which bonds would be weaker than the chlorine bonds? Here's chlorine. I'm looking for weaker, so I'm looking for an energy less than 240 or a length greater than 199. Well, there's only two on this list that are greater than 199 and less than 240 in the energy column. Bromine-bromine and iodine-iodine bonds would be weaker than the chlorine-chlorine bond. Electronegativity. Here it comes again. What is it? A measure of the tendency of an atom to attract bonding electrons to itself. How badly does an atom want to gain another electron? You can have three different types of bonds. You can have no sharing. This would be where one element gives its electron to another. We called that ionic bonds in the last unit. Then you can have two different types of sharing. You can have sharing where this happens 100% equal. That is called a non-polar covalent bond. Or you can have unequal sharing, where in this case the green atom has the electron the majority of the time. It is called a polar bond, polar covalent bond. Here's the trend for electronegativity. Again, fluorine is our highest with a 4.0. You will be given this chart. It's in your cheat sheet in your little packet with your periodic table. Now we're actually going to use these numbers. We don't just need to know the trend, that it increases up because it gets smaller and it increases to the right because we're getting closer to filling our 8 total valence electrons. Now we're actually going to use the numbers to determine what type of bond we have. Here are your three different types of bond again. Non-polar covalent. That's going to give us a value from 0 to 0.5. These are called dipole moments. And a dipole moment is when you subtract the two values of the two elements that you're talking about from this electronegativity chart. If you subtract two numbers and you get between a 0.5 and a 2.1, that's a polar covalent bond. Remember, that's unequal sharing. And if you get a number greater than 2.1, the max should be about 3.3. That's an ionic bond. There's no sharing whatsoever in an ionic bond. So you'll need to know this scale. 0 to 0.5 is nonpolar, 0.5 to 2.1 is polar, 2.1 to 3.3 is ionic. Let's see how we use that. 0 to 0.5 we said was nonpolar covalent. 0.5 to 2.1 is polar covalent, and 2.1 to 3.3 is ionic. Okay. I'm going to do the bottom three. Nitrogen and oxygen. I'm going to look up their numbers. Nitrogen right here is 2.81, and oxygen is 3.37. Now, you're going to subtract them in such a way that you always get a positive number. So 3.37 minus 2.81, where's that going to fall in my category? That's going to be a polar covalent bond. Bromine, bromine, 2.81, just kidding, 2.82, minus 2.82, anything that's diatomic is always going to equal 0. 0 on my scale says it's a non-polar covalent bond. Sorry, we said this one was polar covalent. And lithium and fluorine, fluorine we know is 4.0. Lithium over here is 0.96. 0.96. That gives me a 3.04. Anything greater than 2.1, this is an ionic bond. Push pause now. Work on these three, and we'll go over them next class. Dipoles. What is a dipole? Something that has a dipole has to be polar covalent. So on my scale, it's between 0.5 and 2.1. So of these three examples that I did for you on the previous page, the only one that we had that was polar covalent, and it was only slightly polar covalent, 3.37 minus 2.81 is 0.56. It's only slightly polar covalent. But what does that mean? That means it has a dipole. That means one end is partially positive. The symbol for partially almost looks like an 8, but it's not quite. And the other end is partially negative. So it's not quite ionic. It's kind of like an ion where you have a positive and a negative end, but not quite the whole way. So when you subtract that dipole moment, you get that difference in electronegativity. Again, it has to be between 0.5 and 2.1. The atom with the higher electronegativity value, in this case fluorine, is 4.0, hydrogen is 2.2. Remembering what electronegativity is again, it's the desire to gain more electrons. So of these examples, H and F, fluorine has a stronger desire to gain more electrons. Therefore, the electrons will spend the majority of the time with fluorine. It therefore has a partial negative charge because the electrons have a negative charge. If they're spending the majority of their time on this side of the molecule, it's going to have a partial negative charge. If you have a partial negative on fluorine, hydrogen has to have a partial positive. So each molecule, here's a general example, has a partial negative end and a partial positive end. The end with the partial negative has a higher electronegativity value. The example on the right, this is the partial positive. That says partial negative. That says partial negative. And that says partial negative. So those three must be the same, but they must all have a higher electronegativity value than the red one in the center. So the electrons are being pulled to the outside of that molecule, the three atoms on the outside. Dipole trends. Your dipole moment, again, is your difference in electronegativity. This is where you subtract the two values. That number that you get, the higher the number, the closer, again, 0.5 to 2.1. The greater the dipole moment, the closer it is to 2.1, the more polar the bond. As you increase in polarity, you get stronger. I'm getting closer to looking like something that's ionic because ionic bonds have the strongest bonds. So on our scale that went nonpolar, polar covalent, and ionic, that's weak to strong in order. The higher the number, when you subtract the two and get your dipole moment, the higher the number, the stronger the bond. What does that mean for melting and boiling point? Well, the stronger the force of attraction, the higher the dipole moment, the higher that number is that you subtract. This will be 0. This is non-polar covalent. Water, if you subtract H from O, now we don't need to worry about the fact that this is a 2. We just look at the two elements and subtract H and O. You're going to see that that's a polar covalent bond. And we know, we talked about table salt forever in the last unit, we know that's ionic. So 0 to 2.1, or 0.5 really. 0.5 to 2.1, and then 2.1 to 3.3 is ionic. The higher the number, the stronger the attraction. The stronger the attraction, the higher the melting and boiling point. So these guys would be the strongest, ionic will be the strongest, and therefore have the highest melting and boiling point, which is why this exists as a solid at room temperature. Water is a liquid, and most, bromine not so much, but all the other diatomics exist as in the gas form. Covalent bonding recap. We're sharing electrons in covalent bonds. They share because they're more stable. Shorter bonds are stronger. If you're stronger, you have more energy. It would require more energy to break it. Multiple bonds, triple bonds, are the strongest, then double, then single. Electronegativity, how badly does the atom want to gain another bonding electron? Do you know the trend? And then when you subtract that difference in electronegativity, you get your dipole moment. You can have 3 different types of bonds. They are nonpolar, polar, and ionic. Don't forget to learn the numbers, the scales, and which one fits where. We said the dipole moment was the difference in electronegativity. The dipole means it's unequal. So whenever you have a dipole, it has to be a polar covalent bond. They're sharing, but it's an unequal share. The greater the dipole, the higher the number, the stronger the bond. And then we're going to look at some ionic and covalent characteristics. Here they are in a table for you. Ionic, they're very, very strong. They have high melting and boiling points. Covalents are just the opposite. They're low. Ionic properties dissolve in polar solvents. That's why table salt dissolves in water. Covalent dissolves in nonpolar. These guys are the charged, plus, minus. These are not charged. Ionic, in the liquid and dissolved phase, conducts electricity. Covalent is the opposite. They do not conduct electricity. Liquid phase and dissolved phase can conduct. These guys don't ever conduct. Write down your questions. Let me know what they are, and we'll talk about all of this the next day in class.